Alright, welcome back. So, here is part 2 of sampling distributions and whatnot. So today we're going to go into more of what a sampling distribution is. Yesterday we talked about different kinds of stats and parameters and all that stuff. Today you're going to tell yourself, hold on, there we go. I can distinguish among the distribution of a population the distribution of a sample and the sampling distribution of a statistic. You know, also tell yourself, I can use the sampling distribution of a statistic to evaluate a claim about a parameter. Yada yada yada. And then one more thing. Sorry. You're gonna tell yourself, hold on. Let me check my notes. I can determine whether or not a stat is an unbiased estimator dash of a population parameter. And I can't. So there's a lot, but bear with me. I think it'll be fun. I can describe the relationship between sample size and the variability of a statistic. So really all we are looking at is how do we say things like, well, the average of like the average height of 10 girls is 63.5 inches. So now we're going to look at, well, can we really say that? Like if 10 girls have the average height of 63 inches, can we apply it to the whole world? Does it really matter? Like if these 10 girls were 63? Well, it kind of doesn't, right? Cuz like if I, found a random group of 10 girls, asked them their height, and I got their average was, 64 inches. If I asked another group of 10 girls, would they all be 63 inches? Probably, or not 63 inches, they'd probably be 64 inches, you know? So, how does that help us? Like, why does it matter if, like, these 10 girls are 70 inches, or these 10 girls are 65 inches, or these 10 girls are, 2 inches? Well, it's pretty important stuff. And you're like, why, Mr. Chow? Well, because that leads us to a thing called sampling variability. Sampling variability. Variability. So what is sampling variability? It is the fact. It might be easier if I just type stuff out, honestly. So it is the fact that that the value of a statistic can be, oh hey, check out that autocorrect, can be different in sizes in repeated sampling. This is going to be a pretty definition heavy video, but it should, for the most part, like if we apply those definitions to the examples, it will make everything a lot more clear. So sampling variability is the fact that the value of a statistic can be different in sizes in repeated sampling. So that basically means, like I said, those 10 girls will have different heights than 10 girls that I picked somewhere else. Like, you know, if I picked 10 random Lynn Camp students and asked for how much money their parents make, it would be very different from another group of randomly picked 10 random students. And so sampling variability is the fact that, again, a statistic, it's a hard word to say, is going to be different in all cases of repeated sampling, or in pretty much all cases of repeated sampling. So every time we take a sample of these 10 girls or 10 Lynn Camp students or whatever, we will get a different mean income or mean height each time. Which is that pretty much makes sense, I think. Maybe. So the main important crux of the matter is then, what is sampling distribution? What is sampling distribution? So, a sampling distribution So before we actually get into what sampling distribution is, we actually need to define what a distribution is. Distribution. And that is going to be a list of all possible values a variable can take. So like an example of a distribution, like that would be the GPA of the average GPA, the GPA of a student at Lynn Camp. And that can basically range from 0 to, I guess for a lot of students, I guess like 4.25. I'm assuming that's like the highest GPA. It's probably not. Who knows? 0.425. 0 with a GPA 0 to a GPA 4.25. That represents all the possible values a variable can take. And that would be the distribution of GPAs at Lynn Camp High. It would be, again, all possible GPAs. So like 1, 2, 2.5, 2.67, 2.7725, yada, etc., etc. And so, what is a sampling distribution? A sampling distribution, sampling dist would be all, it's going to be the distribution of values taken by the statistic in all possible samples of the same size. And so this is like if a sampling and distribution of values taken by a statistic in all possible samples of the same size. Here, I will, like, what the heck does that mean, Mr. Chow? Well, let me show you. You guys remember we've been doing those, let's see, existing video, done. You guys know how we've been doing the dice rolling things. Like, why the heck are we doing this, Mr. Joe? Well, if we look at this, I've been having you guys roll the die, 4 dice, and then having you guys find the average, the average of each of the four dice. In this case, the sampling distribution. Let's see, sampling distribution. I just said like 5 times for no reason. Would be all the averages between 1 through 6, and that includes 1, 1.25, 1.5, 1.75, because those are all the possible averages we could possibly get with our 4 dice. Like, we can't get 1.6, we can't get 2.2, but we can get 1.25, 2.25, 3.75, 4.75. And that is what the sampling distribution is. It is all possible values that our samples could take. And in this case, in this dice game that we have, that I had you guys do last semester, well, if you look at that, we have all the possible combinations of numbers to give us all the possible combinations of averages. Hopefully that makes clear, a little bit clearer, what a sampling distribution is. And like, just again, clarity with the sampling variability. Obviously, every single time we didn't get the same number. We got 1.75. We got a bunch of 2s. We got a bunch of 3s. A bunch of 3.25s. Again, that's because sampling variability. You're going to get a different value for different samples. Yeah. Okay. Oh, and it's also important that, like, hey, you guys rolled 4 dice each time. 4 dice. That's your sample size. It was 4, 4, 4, 4. If you remember. And so you get 4, 4, 4, 4 dice each time. Alright. So now, next question is asking us, what is a population distribution? Well, let's see. Population distribution. Pop this. Pop this. It is all possible values. There's all possible values an individual within a population can take. So, sample distributions, we're looking at the value of an entire sample, but with population distribution, we're looking at a single thing. So in this case, again, at the dice, we are looking at an individual dice. We are looking at 1 dice, and all the possible values of 1 dice is 1, 2, 3, 4, 5, 6. This is our population distribution because our dice can only take these 6 numbers. This is really important because sampling distribution is the possible values of an entire sample. This is the possible value of an individual. And then we also have the distribution of sample data. And that is the individual value of a sample can take. So you're like, wait, but didn't we just say that's what the sampling distribution is? Well, no, that is it's sort of different. They are pretty similar, but at the same time they're also very different. So distribution of sample data is the individual value of a sample. So like I rolled a dice and I got a 5.25. That is the distribution of sample data. But the sampling distribution is going to be all the values that a sample can take. A distribution sample is the one value a sample can take. So like a sampling distribution is going to be represents all the averages between 1 and 6, while a distribution of sample data is just, the one average a sample data represents. And that sort of would answer. Also, I don't know what I'm not looking at the sheet right now, but it would answer it would answer that next question after what is the distribution of sample data. Again, sampling distribution represents all of the possible values a sample can have. So that will be sort of the all-inclusive, the umbrella, the giant umbrella. A population distribution is all the individual values a population can take, and the distribution of sample data is the actual individual value a sample is taking. Alright. So now we're going to look at sampling distributions, like how can we make them, interesting. Remember when we talked about distribution early in the year, we used, CUS. And remember, CUS stands for center. So that again is your mean. Like where is the middle of the data? Where is the middle of the data? U is your unusual features. U is your unusual features. Or your outliers. The first S is going to be shape. Like, is it a bell shape? Is it a normal shape? Is it like, woo? Or is it like this? Or is it like this? And then S is your spread. So how spread out the data? What is the variability? How much do all the numbers differ from each other? So like something like this would have a high variability, but something like this has a low variability. And so hopefully you guys remember that from earlier in the year. If not, please return to those notes. And then two more things, I promise you, two more things. You're like, oh my gosh, this video is going on forever. But like, hey, it's worth it. For a sampling distribution to be actually useful for us, it's like what makes, rolling finding 10 girls and asking for their height, like how is that useful for us? Like at what point does it become useful information and say, we can like say things about it? Like, okay, so like I've gathered 10 samples of, like 50 different samples of 10 girls, and all their heights were, like the average height of them was around 60. We can for sure probably at that point say, like, the average height of a woman in the US is 60. So, what makes a sampling distribution useful? So, first it needs to be an unbiased estimator. And, like, what is that? So, that means the mean of the statistic of a sampling. The mean of a statistic of a sampling distribution is equal to the value. if I can type, I can't type right now, is equal to the value of the parameter being estimated. So that means if we look at a bunch of samples, like a bunch of different samples, like if I counted 50 different groups of 5 randomly chosen high school students at Lynn Camp, and I asked for their GPA and averaged them all together. After a while, that average will start to look pretty close to the actual average GPA of our school. So the more times we take of a sample, the closer we get to the true parameter, which is like, it's like, hey, that sounds like familiar. It's like, like law of large numbers. Like the more times we flip a coin, the closer it gets to its true probability. So same thing, the mean of a statistic of a sampling distribution is going to be more equal to the parameter being estimated the more times we take a sample. And then last definition, the last question is asking, what is it asking? It's asking what is, how does sample size relate to sampling variability? Sample size versus variability. Whatever, you get the point. Well, the bigger, how cool is that? I like that. The bigger a sample size is, the smaller variability. Because, well, you're getting more data. You're getting more information. You're making less assumptions. You're getting more information about something. So therefore, it sort of reduces the variability of a sample. But of course, if the data sucks because you asked the first 10 people you saw at Lynn Camp, or you asked everybody who's like under 5'9", like, are you a midget, which would cause voluntary or like non-response bias or something like that. Bad data will still be bad data no matter how many times you collect it. And also, a sample needs, hold on. A pop needs, I'm going to draw a line so it's clear. A pop needs to be 10 times bigger than the sample. So that means if I have a population, like Lynn Camp. Lynn Camp's a small school. There's about 450 people. Like, I would not be able to get a good sample of 50 students at Lynn Camp because there's only 450 of y'all. So my sample size has to be 10 times smaller than the population. So that right there is a lot of information, but we're going to definitely for sure do all the practice in class. But yeah. So try 1 and 2. We'll go over those when we get to class tomorrow. And then, yes. So use all those definitions. Try 1 and 2. I just don't want to, make a longer video and then have you guys zone out. But they are definitely harder problems. But we will go over them in class. But just try them. Alright. Goodbye.